Okay, so we've started our recording. So this evening's speaker is Fletcher Turner. Fletcher is an electrical application engineer at True Insight. He studied electrical engineering and German at the University of South Carolina in Columbia, South Carolina, where he lives and works. In graduate school, he worked in a lab that had research interests in several areas of mechanical and electrical engineering. His major interest was in the intelligent control and development of new algorithms and integrations with neural networks to fuse camera and sensor data for autonomous vehicle navigation. Fletcher has worked with optimizing camera data received from several camera stations at different locations, intelligent predictive maintenance, and anomaly detection in robotics. His love of the new and exciting applications of engineering is what led him to become an applications engineer, where he can interact with a new field or subfield almost every day. His passions and hobbies outside of his professional life include spending time with his family and dogs, traveling the country and globe, and watching all of the Oscar nominations each year. Please mute your microphones at this time, and I'd like to turn this over to Fletcher.
All right. Thank you, Scott. So yeah, as Scott ran through, I have a background, I guess if you had to say broadly, in robotics. So I'm also going to go ahead and turn my camera off for bandwidth. Broadly in robotics, but I had some experience, or some exposure, I should say, to applications engineering, and ended up at True Insight last year. And we'll be today kind of taking a look at what we do at True Insight in a specific case study with the CISPR analysis. I think it is worth mentioning that my background is not in EMC, so you'll have to forgive me if I make a mistake here or there in some nomenclature or some explanation. But we do have one of the authors of the paper that I'll be working through today. He is in the audience, Dr. C.J. Reddy, and he'll be able to help out with some questions that you might have. And so I'm not sure if he will be pinging in the chat, or if we'll save that till the end. But either way, if you see any responses coming from him, that's why. So yeah, let's just jump right over here. So the outline for what I'm going to be doing today is very briefly talking about what CISPR is, because I'm sure most of you already know more than me. So I won't spend too long on that. And then what we'll spend the bulk of the time in is looking at the tool itself, which is FICO. And I'll go over kind of a brief bullet point analysis of what it's capable of. We'll look at some demonstrations in the context of some CISPR 25 and 12 analysis. And then we have some results. Again, this is all from a paper that CJ co-authored. So if anyone's interested, we can share that paper after this meeting. And then, like I mentioned, we'll open it up for questions at the end. So again, like I said, you probably already are all aware, but for anyone who is not, CISPR is, I'm not even going to attempt to pronounce the real name. German is my specialty. So, but in English, it's the International Special Committee on Radio Interference. And long story short, they establish guidelines for electromagnetic compatibility. And so the two that we're going to be looking at today are CISPR 12 and 25. So CISPR 12 establishes the regulation for uninterrupted communication for off-board receivers. And kind of looking at it the other way, CISPR 25 is for the quality of onboard receivers. So we'll take a look at what that means in the context of the problem as we move through this presentation. So like I mentioned, German is my background, so I always take this opportunity to tell people what FICO actually stands for. And it's Feldberechnen für Körper mit beliebiger Oberfläche. It's just fun to say. But again, it's a long name, field calculations with bodies of arbitrary surface. All that means is it's a 3D design and analysis software for specifically for high frequency electromagnetic systems. So we can analyze radio frequency devices, antennas, wireless networks, etc. And there's plenty of different solvers available within FICO. And there's, of course, hybridizations of those solvers. So without any further ado, we'll just jump right in to kind of first, we'll look at what does the FICO interface look like. So just to make sure, can everyone see a new screen that is not my PowerPoint now?
Yes, I can see.
Okay, perfect. So before we start even looking at the model we're using, just kind of wanted to go over a little bit of what how FICO's workflow looks, especially since this might be newer to some people than CISPR is. I know we were talking about it at the very beginning of the meeting that some of you have heard of it, some of you might have even worked with it before, but just for those who are coming in blind, I'll show a little bit what it looks like. So we have our workspace here where we can, just like any other 3D CAD program, we can zoom in and out and look at our model. That's pretty standard. But then we've got this tab at the top that kind of helps us go through the process of designing something that we want to actually analyze within FICO. So here on the Home tab, we've got some pretty standard options. I won't go over a lot of them, but one cool thing that I really like is the ability to import pre-built components. So you see there's a pretty extensive list here of options, and that includes not only the actual electrical components you're trying to model, like for example, a blade antenna or a biconical antenna, but also some actual structures so you can analyze how they interact in more real-world scenarios. So for example, if we wanted to do some antennas on a plane, we could pull in a plane model right here. I won't actually do that because that would mess up the model I currently have open. But there's a lot of options here, a lot of different devices, and a couple of different options for vehicles and quadcopters even, and also an actual truss if you wanted to build a tower and plug it in somewhere. And this could be beneficial with another tool that I won't be spending any time on, but you can always reach out to us with more questions if you are curious. We have another tool called WinProp that works with FICO, where you can design antennas and devices within FICO and then actually test them in larger scale environments, ranging from say an office space. Say you had you wanted to optimize your Wi-Fi router position in your office building, all the way up to building a cell phone tower within a city, and you want to optimize the position and orientation of that that tower in a specific city, given that the data for that to model the location. So moving on, we don't just have these components built in. You can also import components that you've built in any other CAD software. You can create schematics which look like this right here. And I'll go over what we're using this for momentarily. But then through the design process, go back to 3D view, we've got a bunch of options for actually starting to build things within FICO itself, building something custom without importing or using something pre-built. So again, just like a lot of other CAD softwares, we've got pretty standard shapes. Then we can make unions or subtract, almost like you're about to build something to be 3D printed. You can make lines or helices, any sort of curve, and then sweep a 2D shape along that curve to create a 3D shape. So the options are pretty limitless depending on whatever you want to come up with to try to build. And then on top of that, you can actually define various media for the things your elements to be made out of. So it comes with a couple already pre-built. It comes with a perfect electric and perfect magnetic conductor. Then if you want to import some custom dielectric, for example, you can just bring this up. You can define it number of different ways, plug in its loss tangent, relative permittivity, give it a name, mass, and highly customizable there. And you can give it a color too to make it more obvious. Some of these colors might not be what I would have picked, but that's okay. And then moving forward, we can transform it. That's not as exciting. So we'll skip right over to adding sources and loads to our model. So this is where we start actually getting into what the software is designed for and capable of. So we can add different ports, that edge ports, wire ports, waveguides, microstrips, all sorts of options. Depending on the solver, you might need, a FEM port. You can define different sources and loads. And again, I won't actually go through any of these because we've already got everything set up that we want to run. But one thing that is really cool is when you are doing your request, which is now where you're telling it what you want to pull out after you've given it all the information that it needs, you can get different configurations. And this way you don't have to create an entire new model. If you want to look at two specific frequencies, you can do two configurations, and each one will have that frequency. Same goes for sources, loads, power. Then we can look at all sorts of output data that we might be interested in, near fields, far fields, surface currents, S parameters. Really, if it's EM, FICO can pull that information for you. It can solve that for you. And one other cool thing that it does, again, we didn't actually run through it in this one, but we can add some optimization parameters where we can either search for combinations of parameterized variables. We're trying to find optimum output based on whatever we're trying to minimize or maximize. Again, there's loads of options here, but it's very intuitive. Or you can even, if you have a specific data set that you are trying to mimic, you can add a mask, import that data set, and the parameters you want to, vary, and it will try to find the inputs that give you that output you're looking for. So a lot of functionality there. Last thing before actually solving is the meshing. So FICO has a pretty powerful built-in meshing tool already, but there's plenty of options to customize that as much as you want. So I typically, for demos, just stick with the standard mesh size, but you can get as complex as you like with defining shapes and how fine or coarse you want that. So then lastly, we would jump into solving and running something within FICO. And so again, we've got a couple more options we can do. We can define some symmetry if we're working with maybe a waveguide or something that has electric or magnetic symmetry that will help us speed up the solution. We can enable numerical Green's function. We've got a boatload of solver settings that I won't go into, but basically you can tell this program to do whatever you need it to do based on the problem at hand. You can select the solver you want, the resolution, all that good stuff. So then the last thing to do would to actually be to run it and launch our other tool, post-FICO. So I'll go ahead and show an example of what post-FICO looks like as well. So in this case study we're looking at, we're doing CISPR analysis, CISPR 25 and CISPR 12. So what we have here is the realized gain of a biconical antenna that we made for this study. And this is, it's very easy to use this program right here. Let me pull this out. So if I just get a new Cartesian graph, I can take that data and I've got plenty of options over here for how I want to view this. So we can convert it to dB. We can, if we want to enable math, didn't do any of that for this specific project, but say, for whatever reason we have a trace that we want to shift up by 10. It's as easy as typing just plus 10 right there, and it shifts the whole thing up. But we will just turn that back off. But so yeah, right off the bat, we can look at our gain data. And let me jump over to the slides for just a moment. I am a little bit out of order, sorry about that. So we've got that same plot right here. And then we can export this data in a CSV and get our antenna factor. Unfortunately, there's not really a direct way to do this in FICO, but it's pretty straightforward to export this data and get this information in whatever other data processing tool you might have on hand. The other thing that I should mention is the actual motor that we're using in this study. So I should have said this earlier. So for our CISPR 25, we're looking at a 2-speed DC wiper motor. So we actually have that modeled in our schematic right here. That's what this is. And then we've got it connected to a couple other components that we'll circle back to. But again, we can use FICO to pull that motor impedance across a range of frequencies and plot that however we see fit. So let me, and one other thing that we didn't, that I don't have in FICO pulled up, but for the higher frequencies from that 200 megahertz up to gigahertz, we used a log periodic dipole array antenna and just analyzed the same way we analyzed the biconical antenna. So jumping back into FICO, sorry, I've got about 20 different tabs of FICO pulled up. So it'll take me a second to navigate to the correct one each time. So again, what we have here is this is our setup for the radiated emission testing. And this is for 30 megahertz up to 200 megahertz. So here you see we have our vertical biconical antenna next to our, this is a DC motor with our, excuse me, I've lost my place here. Our DC motor with our line impedance stabilizing network and our actual test harness over here. And so that's what we're looking at on this table. And we can see that we've got this face. If I click on that, it will pull up. You can see that we're just resting on a perfect electric conductor. I believe there were supposed to be some legs on this table made out of wood. I might have accidentally deleted those before this presentation. My apologies. So, and with this, we can define a lot of different parameters. We can go in more detail about what kind of cable we're using, and we'll look at some of those in the results from the paper. But just to look at how they actually look in post-FICO, we can come over here. And what we're looking at here is the, well, this is the load voltage received by the electric field received by the biconical antenna. And again, we just took our, we can just hide that. And we just took that over here, and we can take a look at a couple of different options. Obviously, impedance will be pretty boring because this was designed to have a 50 ohm impedance. But we can take a look at some other more exciting piece of information. And again, look at that in whichever format is necessary at that time. So in this study, this looked at a comparison between a couple of different kinds of cables, looking at the radiated or the E field received by that motor based on what that cable was. So you can see that we've got this vertical orientation, which is what was shown in FICO earlier. We also have horizontal, where we just flip it on its side, basically in place. And we've got 4 different kinds of cables for each one. And obviously, as expected, that that twisted pair with the LC filter does the best. Doesn't look like with the horizontal that any of them really pass the class 3 or 5 limits. But with the vertical, looks like definitely the twisted pair with the filter does, and possibly the twisted pair in the RG214. So depending on your which class limit you're using, could help you decide which of these would be the appropriate setup to use when you move from simulation to production. All right, so let's pull this up. Again, sorry, I've got too many CAD FICO pages pulled up. Okay. So, oh, sorry, that was the wrong thing. Oh, sorry, yep, I already had it up right here. So again, we looked at the same thing for the higher frequency with the LPDA antenna. And again, we can see that the twisted pair does the best against RG4 and RG214, but none of them pass those limits for class 5 at least with the horizontal. But the vertical, we are a little bit more forgiving. So again, that could help us in the design phase. So let's see. All right, here, this is for the conducted emission test setup. So again, just have our cable harness, our motor, and our line impedance stabilizing network. So this is our where our DC motor is, and this is where the LISN and the voltage source are. So again, I think that there were originally some wooden supports underneath this perfect electric conductor test plane. I'm not sure what happened to those. But then again, we can take a look at the conducted emission from that setup right there. And one nice thing, you'll see that this, I've already done it right here, but I'll show kind of what it looks like from scratch. So if I just get a new plot and plug that probe in, you can see the plot is pretty hard to read right now because it's not logarithmic, but it's pretty easy to swap that over. So, well, if I can find the button. I say it's easy, and then I can't find the button. There it is. Log horizontal and dB. And we've got a couple options for customizing our plots in post-FICO. We can just as easily click and drag and move things around, or we can pull up our axis settings, turn off the auto, plug in whatever we are interested in. Same for vertical. And all these, if we go to chart text, we can also customize what our labels are to make this more readable, which is where most of the plots came from in the slides. I just haven't taken the time to do that within post-FICO because we have those results handy for us right here. Oh, that is, sorry, let me click back. My apologies. Okay, so our last setup within CAD FICO, we'll swap back over to the CISPR 12 analysis. So this will be looking at how our model behaves with an actual antenna on top of the car with a DC wiper motor, 2-speed DC motor placed at the back. So again, this is probably the more complex of the, at least from a modeling perspective, of what we've looked at so far. One thing you don't see in this model is, sorry, I keep left clicking or right clicking instead of left clicking, we've got, we actually tested with different placements of this monopole antenna on top of the car. We had it right here where you see it, and then also right here at this next intersection. So we could, I don't think it will let me move anything right now because it's all unioned. Yeah, but we could pull this up right here and we would know exactly where we wanted to move it. We could plug in its new coordinates and actually move that to its new location for comparison's sake. So that's exactly, well, for in post-FICO, the results we're looking at are actually just for the first placement, the one that you actually see. But then we also have some results handy for looking at that with the other placement that I pointed out. So again, you could see that interference between the DC motor on board and the receiving antenna. So this could be helpful for figuring out, in this 820 to 960 megahertz range, making sure that the quality of the received antenna signal is what we want it to be, and that we're not going to mess it up with whatever devices we might have. And one of the things that's worth pointing out on that model is, again, the cable harness setup. So we've got our DC motor and then the connections in the car. So we can click and drag around here. So one pretty cool feature about this cable harness setup is you'll probably see this gray line right here. And if you're anything like me, you probably are looking at that and thought, what is that for? At least that's what I thought when I very first looked at this schematic. But then if we take this model and let me turn the opacity. If we take that and position it just so, oops, sorry, I keep trying to get it there we go. That shape starts to look pretty familiar. So I just thought that's not really, anything all that exciting, but I thought that was a pretty neat little feature. So then let me put that back over there. Okay, and so lastly, we can take a look at our absorber lined shielded enclosure setup. So that was pretty similar to what we actually just looked at the last model. But now what we have here are some other receiving antennas, and we can measure the radiated disturbances seen by these biconical antennas. So again, we've just got our setup with our motor and our ALSE, and we can take a look at the results that FICO can provide us there for our CISPR 12 analysis. So again, in that range from 30 megahertz up to 200 megahertz. So we've got, you'll see it says position 1 and 2 here. That's referring to the positions of those antennas in the model. So this would be position 1 and 2. We're no longer looking at the monopole on top of the car. That back. And so again, we could use this to help us decide what kind of next steps are necessary what kind of next steps are necessary in the design and analysis phase. So I know that went by pretty fast. Again, there's a great deal of the EMC end that is a little bit harder for me to elaborate on. But as far as the FICO and post-FICO, CAD FICO, a lot of FICO interfaces, I can start accepting questions on that or any specific questions on the study. I think CJ is still in here to help out with that. So with that being said, I'll open up the floor.
Okay, great. Thanks so much, Fletcher, for your presentation. Yeah, this time, feel free to unmute or turn on your camera and pose your questions to Fletcher. And if it's an EMC question, we can get CJ in here as well.
Yeah.
Here's in the chat window. Can you see the chat window, Fletcher?
Yes.
Down in the center. Yeah,
yes.
Pop that open if you would. There's a question for you there.
Okay.
So you want me to read it to everyone, or can you?
Yeah, I'll read it out loud for everyone.
Okay.
So we've got Ryan asking, could you briefly describe the coarsening of a high poly model down to something that's less computationally expensive, but still useful? For an automobile, the original model could be millions of polys, for example. The car in this model seems to have been simplified quite a bit. That is, let me pull up I have one of the models open with the mesh showing. Let's see. There we go. So yeah, you can see you can define different coarseness and fineness based on the shapes of the model. So one of the nice things that the solver automatically does, especially for these larger models, is for some of these larger, more uniform surfaces, we get the larger triangles for the simulation breakdown, and it will automatically get finer in more complex areas. So it kind of is a little half and half of, here, I'll zoom in. You can see it gets finer for these curved and more intricate surfaces. So it kind of bridges that gap for you of maintaining computational speed as well as maintaining fidelity of the model.
Let me throw in a question. So if you had a wireframe model from your OEM, could you import that into here? Is that something you can do with this?
So yeah, there's a lot that you can import into CAD FICO. I guess I'm a little unfamiliar with what file type that would be. But
maybe if I can make a comment, Fletcher.
Okay, CJ, yeah, go ahead.
Yeah. So a couple of things I wonder. First, I think maybe Ryan's question, I guess, on bringing a very complex model into FICO with various entities, right? I mean, hundreds and millions of entities. We do have an import, I think, as Fletcher is pointing out there, of any format you can think of, CATIA, STEP, IGES, and those kind of things we can bring in. But of course, CAD FICO itself is, though it can do some kind of simplification, but it's not, suited just for the simplification purpose. We do have an Altair portfolio, other tools called HyperMesh and other things, widely used in automotive industry to de-feature. I think that's what we call, I guess, take out all the small parts. I just want to know, just want to have, let's say in this case, body in white, right? No seats, nothing, I guess, inside. So we can easily clean up there and then bring that into FICO for analysis. Scott, when you said the wire model, I don't know how many people use wire models nowadays. It used to be in a very old.
The model similar to this one that they may have already. They may have.
Yes, yeah. If there is a CAD model, we can always import. Whenever we say wire model, I remind myself of the neck days, I guess.
That's not what I meant. Sorry, that's not what I meant.
So, by the way, I think we can also import neck models into FICO. If you have them there. Yeah. Thanks, Fletcher.
Thank you, CJ.
There's another question in the chat if you want to scroll to the next one.
So yeah, we've got one. Have you ever performed any empirical measurements? Again, I'll let CJ touch on this, but this was all done in sim. Unfortunately, these aren't, this specific analysis isn't compared against any empirical data. But I don't know if you've got anything else to add to that specific point, CJ.
Yes, yeah, you're right, Fletcher. I think, Keith, I think we have not measured. I mean, this is, of course, to show the process, how you can do it. It's possible that when we did that, maybe we're not put right parameters and those kind of things, because we're just trying to show the process. But I think if you put the right parameters, probably it'll work very well and should compare with the measurements. That is something, we can work with any of you, I guess, who may be interested in validating the simulations with the measurements or vice versa.
Thank you.
And there's another one
one
from
for-
Jerry.
Yep. So Jerry asked the motor noise source. That's a mouthful. A brush motor is a coarse broadband noise source. How did you get the passive elements RLC and the sparking noise source to become a frequency swept sinusoid?
Well, let me explain. Yeah, I mean, my impression is that you don't actually have a spark source from the commutators. I assume it's a brush motor, which has broadband noise, but it has a very strange frequency response in addition to the RLCs of the wires and the other physical parts. So my impression is that perhaps you just took the passive components and then added a swept sinusoid frequency to get a kind of a rough idea. And maybe the sinusoid is a constant versus frequency, just again for a sense, but it certainly doesn't match the real world situation as the previous question, which was, have you validated it against real world stuff?
Right. I'll let me pull that up. And again, CJ, I'll let you talk about this. I know that.
Yes, yeah.
Okay.
Jerry, nice seeing you as well here. Hopefully we'll see you in Grand Rapids, I guess, right? In EMC. You're right. I think what we took here is a model that's available in the literature. I think in the paper we published, I guess, there's a reference to this motor where they used it for their own simulations. So we picked from there and put it here. Because the point here is that, if we have a more realistic motor model and also the excitation, we can do that as well. Just that our knowledge of this is a bit limited, so we picked whatever is available in the literature.
Yeah, that's fair enough. Very good. Thank you.
Yeah, I do think maybe this is a good demonstration is that when you're doing any of this modeling, you need to be semi-aware of what you expect to occur. The thing that got my attention was, if I caught it correctly, you were giving indication that a twisted pair would give better performance than RG214, like 500-600 megahertz. That tells me that the model probably was not considering the common mode currents, which will dominate at those higher frequencies. And a twisted pair absolutely is not going to perform better than RG214 under those circumstances. But nevertheless, if the model, it's as good as the model, and then I understand it, and it demonstrates how to use the tool.
Yes. Thanks.
Thank you.
Okay, is there any more questions at this time? Okay, not hearing any. I'm going to stop the recording at this time, and then we're going to move on over to our drawing as soon as I can find the stop button. Here we go.